Step into a machine shop in Newark, New Jersey, in the year 1882. The shop belongs to a company called Watts, Campbell and Company, and it builds Corliss steam engines. There are about 40 men working on the floor right now, and the noise is constant. The ring of hammer on iron. The slow grinding of a boring bar turning inside a cast iron cylinder. The hiss of steam from a belt-driven line shaft that runs the length of the ceiling, powering every lathe, every planer, every drill press in the room. Among these men is a master machinist. He is in his late 40s. He has been working metal since he was 15 years old, when he started as an apprentice, sweeping iron filings off the floor of this same shop. He cannot read. He never learned. But he can measure a bore to within 1/64th of an inch, using nothing but a pair of calipers and the calloused tips of his fingers. Right now, he is finishing the cylinder for a 200 horsepower Corliss stationary engine. The cylinder is a piece of cast iron roughly 6 feet long and 2 feet across. It weighs close to 3 tons. The inside of this cylinder must be perfectly round, perfectly smooth, and perfectly straight, to a tolerance of 1/64th of an inch over its entire length. If it is not, the piston will not seal. If the piston does not seal, the engine will not hold pressure. If the engine does not hold pressure, a brewery in Pennsylvania will not have power, and the men who work there will not have jobs. He is doing this work by hand. Files, scrapers, lapping compound made from ground emery mixed with oil. He works the interior surface inch by inch, day after day, for 3 weeks straight. When he is finished, the surface is so smooth that a piston ring slides through it under its own weight without catching or binding anywhere along the way. He has built dozens of these cylinders over his career. Each one of them ended up in a factory or a mill or a pumping station somewhere in America. He never signed his work. Almost no one in this trade ever did. This is how America built every steam engine, by hand. And to understand what that actually meant, you have to understand the scale of what America needed these engines to do. By 1880, the United States was not just using steam power. It was addicted to it. The federal census of 1,838 had counted just over 3,000 steam engines in the entire country. 350 of those were on locomotives. 800 were on steamboats. The rest were stationary. That was the whole of American steam power in 1838, and it was already reshaping the economy. But by 1880, 42 years later, the number had exploded beyond anyone's ability to easily count. Conservative estimates from the Census of Manufactures put the number of stationary steam engines alone at well over 50,000. The railroad companies were operating close to 20,000 locomotives. Steamships carried goods up and down every navigable river and across both oceans. And every single one of those engines, every cylinder, every crankshaft, every piston rod, every connecting rod, every valve assembly, had been built by hand in a machine shop, not in one shop. In hundreds of them, scattered across the industrial Northeast and Midwest. Pennsylvania alone had more machine shops per square mile than most European countries. New Jersey, Rhode Island, Massachusetts, Connecticut, New York, Ohio. These states were the engine rooms of American industry, and within them, the machine shops were the engine rooms of the engine rooms. A single large Corliss engine for a textile mill might contain over 1,000 individually machined parts. A locomotive was even more complex. And America was consuming these machines at a rate that kept every shop in the country running at full capacity for decades, not assembled from standardized parts, not stamped out by automation, built, fitted, adjusted, filed, scraped, lapped, by men who learned their trade through years of apprenticeship and decades of repetition. Think about that for a moment. In 1880, if a textile mill in Lowell, Massachusetts, needed a new engine, a shop in Providence or Newark or Philadelphia would cast the parts, machine them, hand fit them, test them, disassemble them, ship them by rail, and then send a crew of fitters to the mill site to reassemble and align the engine on its foundation. The entire process, from order to operation, could take 6 months to a year for a single engine. And America needed thousands of them every year. So who were the companies that actually built these things? Where were the shops? And who were the men inside them? The biggest name in American steam engines in the 1870s and 1880s was George Henry Corliss, and the company he built in Providence, Rhode Island. Corliss was born in Easton, New York, in 1817, the son of a doctor. He left school at 14, worked as a clerk, opened a store, got bored, invented a boot stitching machine, and then moved to Providence in 1844, looking for someone to manufacture it. He never built the boot stitching machine. Instead, he walked into the shop of Fairbanks, Bancroft and Company, got hired as a draftsman, and immediately became obsessed with improving the steam engine. Within 4 years, Corliss had redesigned the valve mechanism that controlled how steam entered and exited the cylinder. His innovation, patented in 1849, used separate inlet and exhaust valves with a variable cutoff controlled by the governor. The result was an engine roughly 30% more fuel efficient than anything else on the market. That single improvement freed American industry from its dependence on water power. You no longer had to build your factory next to a river. You could build it anywhere there was coal and a railroad, which, by 1870, was almost everywhere. The Corliss Steam Engine Company grew until it occupied 9 acres in Providence and employed over 1,000 workers. They built engines for textile mills, rolling mills, pumping stations, and sugar refineries from New England to Cuba. And every engine that left the Corliss works was hand-fitted by machinists who had spent years learning how to make cast iron behave. The precision of that work was not abstract. During the Civil War, the Union Navy needed the turret bearing for the ironclad Monitor machined to specifications that no factory in New York could achieve. The bearing, a massive ring on which the gun turret would rotate, was rushed by train to Providence, machined in the Corliss works, and returned to the Brooklyn Navy Yard the same day. The Monitor went on to fight the Merrimack in the first battle between ironclad warships, and the turret that made the Monitor effective was able to rotate because machinists in Providence could hold a tolerance that machinists in New York could not. But Corliss was not the only builder. In Newark, New Jersey, the Watts Campbell Company had been building Corliss-type engines since the 1860s. Founded in 1851 by William Watts and Zachariah Belcher as a small metalworking shop near the city reservoir, the company grew after Daniel T. Campbell joined the partnership in 1865. By the 1880s, Watts Campbell employed around 300 men and was one of the largest machine shops in Newark, supplying engines to breweries, tanneries, thread mills, and electrical companies throughout the Northeast. Their shop on Ogden and Passaic Streets still had its original wooden roof trusses and overhead cranes more than a century later. Some of the machines on that floor dated to the 1860s and 1870s, and they still worked. In Philadelphia, the picture was even bigger. Baldwin Locomotive Works, founded by Matthias W. Baldwin in 1831, had grown into the largest locomotive manufacturer on Earth. Baldwin himself had started as a jeweler's apprentice at 16, moved into manufacturing bookbinding equipment, built his own steam engine when the one he bought proved unsatisfactory, and then turned his attention to locomotives when he saw the commercial opportunity. His first locomotive, Old Ironsides, was built under extraordinary conditions. There were so few skilled machinists in Philadelphia at the time that Baldwin had to teach his workers how to do almost every operation. The cylinders were bored using a chisel fixed in a block of wood, turned by hand. Baldwin did much of the work himself, designing, machining, and assembling the engine in a small shop on Minor Street. By the 1880s, the operation had transformed beyond recognition. Baldwin Locomotive employed 3,000 laborers at its North Broad Street factory and produced nearly 600 locomotives a year. Each of those locomotives contained hand-fitted cylinders, hand-scraped bearings, hand-aligned connecting rods. The company shipped engines to Russia, to Australia, to Central Europe. It was, by the 1880s, the nation's largest locomotive manufacturer, and it would eventually produce over 70,000 locomotives before the age of diesel made steam obsolete. And there were dozens more. Alice Chalmers in Milwaukee, Westinghouse in Pittsburgh, the Rhode Island Locomotive Works, the Grant Locomotive Works in Paterson, New Jersey, the Rogers Locomotive Works, also in Paterson. Every one of these operations depended on the same thing. Not capital, not raw materials, not even engineering talent, though they needed all of those. What they depended on, more than anything else, was the skill of the men who worked the metal. And the way you became one of those men was through an apprenticeship that would, by modern standards, seem almost medieval in its demands. If you wanted to become a machinist in 1875, you started young. 14 or 15 years old was typical. You presented yourself at the door of a machine shop, and asked for an apprenticeship. If you were accepted, you signed an agreement, sometimes a formal indenture, that bound you to the shop for a period of 4 to 7 years, depending on the trade and the era. 7 years was the old standard. By the 1880s, 4 years was becoming more common in the larger shops, though the smaller ones still held to longer terms. Your first year was spent doing nothing of real consequence. You swept floors. You carried tools. You fetched materials. You watched. If you were lucky, an older journeyman would explain what he was doing while you held the lamp or handed him a file. You were paid almost nothing, maybe 50 cents a day, barely enough to cover your board. In your second year, you started working metal. Simple jobs first. Filing flat surfaces. Turning straight cylinders on a lathe. Learning to read a caliper, a micrometer, a straight edge. Learning the feel of different metals under a file. How cast iron cuts differently than wrought iron. How brass wants to grab the tool if you push too hard. How steel will burn your file teeth if you do not keep them clean. By your third and fourth years, you were doing real work under supervision. Fitting bearings. Boring small cylinders. Cutting threads on a lathe. Learning to scrape a surface flat to within thousandths of an inch, using a hand scraper and a surface plate smeared with Prussian blue. This was the heart of the machinist's art. The ability to create a perfectly flat surface using nothing but a sharp piece of hardened steel and the sensitivity of your own hands. You would scrape, check the surface against the blue, see where the high spots were, scrape again, over and over, for hours, until the blue showed an even pattern of contact across the entire surface. By the time you finished your apprenticeship, you were a journeyman machinist. You owned your own tools, a set that you had been accumulating over your years of training, and that represented a significant investment. A good set of machinist's tools in the 1880s, including calipers, micrometers, files, scrapers, surface gauges, and specialty instruments, could cost the equivalent of several months' wages. A machinist's tool chest was his most prized possession. It went with him from shop to shop, and it was never loaned and never touched by another man without permission. You could work anywhere. You could walk into any shop in America, open your chest, lay out your tools, and start producing work to the standards expected by the trade. Master machinists, the men with decades of experience who could take on the most demanding jobs, were treated with a respect in the shop that bordered on reverence. The foreman did not tell a master machinist how to do his work. He told him what needed to be done and when it needed to be finished, and then he left the man alone. This was not courtesy. It was acknowledgement that the master machinist knew more about his work than anyone else in the building, including the owner. The daily wage for a skilled machinist in 1880 ranged from about $2.50 to $5, depending on the shop, the city, and the man's reputation. A master machinist at the top of the pay scale could make $5 a day or more, which was extraordinary money for manual labor. A common laborer was making $1 to $1.50. A machinist was making 3 times that, and he was worth every penny, because the work he did could not be done by anyone who had not served the years. But even the best-trained machinist was nothing without his tools. And the tools of an 1880s machine shop were a combination of massive belt-driven machines and hand instruments of remarkable precision. The primary machine tool was the lathe. By the 1880s, engine lathes could turn cylinders 6 feet long or more, driven by leather belts running from an overhead line shaft. The line shaft itself was powered by a steam engine, which meant that the machine shop ran on the same technology it was building. The lathe held the workpiece and spun it while a cutting tool, clamped in a tool post, removed metal in thin spirals. A good machinist could hold a diameter to within a few thousandths of an inch on a lathe, but the final fitting was always done by hand. The planer was used for flat surfaces. It was a massive machine, sometimes 20 feet long, with a table that moved back and forth under a stationary cutting head. The boring mill was used to bore out cylinders. The drill press drilled holes. The shaper cut keyways and slots. All of these machines were essential, but all of them were crude by modern standards. They got the work close. The machinist's hands got it right. For a large cylinder, the process went something like this. The cylinder was cast in a foundry, poured as molten iron into a sand mold. When it came out of the mold, it was rough. The inside surface had sand inclusions, porosity, uneven shrinkage. The boring mill would take the first cuts, removing the worst of the roughness and bringing the bore close to its final dimension. Then the handwork began. The machinist would coat the inside of the cylinder with a thin layer of lapping compound, a paste of ground emery or corundum mixed with oil. He would work this compound across the surface using a lap, a close-fitting tool wrapped in soft metal or leather, moving it back and forth in long, controlled strokes. The compound would cut the high spots and gradually bring the entire surface to a uniform finish. Between sessions of lapping, he would check the bore with calipers and with a straight edge, looking for any deviation from round, any taper, any spot where the surface was not perfectly true. This process could take days for a small cylinder and weeks for a large one. The sound of it was distinctive, a low, rhythmic scraping that went on for hours without pause, the kind of sound that sank into the walls of the shop and into the bones of the man doing the work. The smell was iron dust and oil, a metallic sweetness that hung in the air and coated everything within 20 feet. A machinist, doing hand-lapping work, would go home at the end of his shift with his hands black from compound, his fingernails permanently stained, the smell of iron so deep in his skin that no amount of washing would remove it. The cylinder for a big Corliss engine, 4 feet or more in diameter with a 10-foot stroke, represented weeks of hand labor from a machinist who could not afford a single mistake. If he went too deep in one spot, if he lapped unevenly, if he left a scratch in the finished surface, the engine would leak, and a leaking engine was a failed engine. There was no tolerance for failure, because there was no way to fix it short of starting over with a new casting. And a new casting meant another pour, another 3 or 4 weeks of cooling and annealing, another month of rough machining before the handwork could begin again. A ruined cylinder was not just a waste of time. It was a waste of the foundry's time, the rough machinist's time, the company's money. A master machinist who ruined a cylinder would carry that shame for years. The same hand fitting applied to every other critical surface on the engine. The crankshaft bearings were scraped to fit, the crosshead guides were scraped to fit, the valve seats were lapped to seal. The piston rings were individually fitted to each cylinder. Nothing was interchangeable. Every engine was a one-off, a unique assembly of parts that had been made to work together by the hands of the men who built them. And those men paid for their skill with their bodies. Machine shops in the 1880s were places of extraordinary danger. The overhead line shafts that powered every machine in the room ran continuously, and the leather belts that connected them to individual machines were open, unguarded, and lethal. A loose sleeve, a dangling apron string, a moment of inattention, and the belt would catch and pull a man into the machinery before anyone could react. Belt injuries were among the most common causes of death and dismemberment in American factories. A man caught by a belt did not survive intact. He was pulled into the pulley and wrapped around the shaft, and what came out the other side was not recognizable as a human being. The lathes themselves were dangerous. A workpiece that came loose in the chuck became a spinning projectile weighing anywhere from a few pounds to several hundred. A cutting tool that grabbed could shatter and send steel fragments across the room at the speed of a bullet. Chips of hot metal flew continuously during cutting operations, embedding themselves in skin, in eyes, in any exposed surface. Eye injuries were so routine that most machinists over 40 had damaged vision in at least one eye. There were no safety glasses. There were no guards on the machines. There was nothing between the man and the metal except his own attention and his own reflexes. The boring mills presented the same hazards at a larger scale. A boring bar that snapped under load could whip across the shop floor. A casting that shifted on the table during a cut could throw the tool and the tool post with enough force to kill a bystander. Men worked around these machines every day, all day, for their entire careers, and they developed an instinct for danger that was as much a part of their training as their skill with a file. You learned where not to stand. You learned what sounds meant trouble. You learned to watch the machine the way a sailor watches the sea, constantly, because the moment you stopped watching was the moment it would kill you. But the most dangerous part of the engine-building process was the forge and the foundry. The forge was where crankshafts and connecting rods were shaped. A large crankshaft might weigh several tons and had to be heated to white heat over 2,000 degrees Fahrenheit before it could be worked under a steam hammer. The men who handled this metal worked with tongs and hooks, standing as close to the glowing mass as they could tolerate, turning it, positioning it, holding it while the hammer fell. Burns were constant. Severe burns were common. Fatal burns were not rare. In the foundry, molten iron was poured at temperatures above 2,500 degrees. A spill, a crack in the mold, a pocket of moisture in the sand that flashed to steam on contact with the liquid metal, any of these could kill a man instantly. Foundry workers wore heavy leather aprons and boots, but had no face shields, no heat-resistant gloves, no protective equipment of any modern kind. The death rate in American foundries in the 1880s was among the highest of any industrial occupation. Hands were the most common casualty. Machinists lost fingers to lathes, to planers, to drill presses. Foundry workers lost hands to pour spills and mold collapses. Blacksmiths lost fingers to steam hammers. These injuries were so common that they barely warranted mention in the shop records. A man who lost a finger came back to work when the wound healed, if it healed. A man who lost a hand was finished. There was no workers' compensation. There was no disability insurance. There was nothing. And yet these men, with these tools, in these conditions, built some of the most remarkable machines the world had ever seen. The crown jewel was the Corliss Centennial engine of 1876. George Corliss himself designed it for the Centennial exhibition in Philadelphia, the great celebration of America's 100th birthday. He spent over $100,000 of his own money on its construction, and he refused to charge the exhibition a cent for it. The engine was a duplex, 2 cylinders, side by side, each bored to 44 inches in diameter with a stroke of 10 feet. It stood 45 feet tall from the floor of Machinery Hall to the top of its walking beam. The flywheel was 30 feet in diameter and weighed 56 tons. The crankshaft was 18 inches in diameter and 12 feet long. The complete engine, when assembled, weighed 700 tons. It was built entirely in Providence, in the Corliss works, by machinists using hand tools. Every cylinder bore was lapped by hand. Every bearing was scraped by hand. Every valve seat was fitted by hand. When it was finished, it was disassembled and loaded onto 65 railroad flat cars for shipment to Philadelphia. On the 10th of May, 1876, nearly 190,000 people flooded the fairgrounds. A choir of 1,000 voices sang the Centennial hymn composed by John Greenleaf Whittier. A band of 150 pieces played the Centennial March, composed for the occasion by Richard Wagner himself. President Ulysses S. Grant and Emperor Dom Pedro II of Brazil walked together to the engine platform, climbed the stairs, and each pulled a lever. The great engine shuddered, hissed, and began to turn. The flywheel, 30 feet across, picked up speed, slowly at first, then faster, until it was turning at 36 revolutions per minute, with a smoothness that seemed impossible for something that weighed 56 tons. The connecting rods rose and fell. The walking beam rocked overhead like the arm of some enormous creature drawing breath. And through more than a mile of underground shafting, 800 machines throughout the 13 acres of Machinery Hall came to life simultaneously. Looms began to weave, saws began to cut, presses began to stamp, pumps began to move water, printing machines began rolling newspapers. Somewhere in that vast hall, a young Alexander Graham Bell was demonstrating a device called the telephonic telegraphic receiver, and Emperor Dom Pedro, who had wandered over to see it, put his ear to the speaker and heard Bell reading from Hamlet. "My God, it talks," the emperor said, and the power that ran through the wire that carried that voice came from the engine that George Corliss had built by hand in a shop in Rhode Island. William Dean Howells, the American writer who was there that day, could not find adequate words. The engine, he wrote, was an athlete of steel and iron. It was the symbol of everything America believed about itself in 1876, that raw material and skilled labor and individual genius could produce wonders that the old world could not match. The Corliss Centennial engine ran flawlessly for 6 months. Every day, all day, it powered the entire exhibition without a single failure. When the fair ended, it was disassembled and shipped back to Providence. 7 years later, George Pullman bought it for $62,000 and installed it in his factory town outside Chicago, where it ran until 1910, 34 years after it was built. And then it was sold for scrap, $7,892.50. That is what the Pullman Company received for the greatest steam engine ever built by hand at the end of its life. Less than $8,000 for 700 tons of precision iron. The engine that had been started by a president and an emperor, that had run flawlessly before 10 million visitors, that had been called systematical in greatness, beautiful in form and without fault, in every detail, a masterpiece by Professor Ratinger of the Polytechnic School of Vienna, was melted down and poured into new shapes that no one would ever remember. George Corliss himself did not live to see it scrapped. He died in Providence on the 21st of February, 1888, at 70 years old. By then, his company employed over 1,000 people and had produced thousands of engines. The American Academy of Arts and Sciences had given him the Rumford Medal. The Institute of France had given him the Montyon Prize. The King of Belgium had made him an officer of the Order of Leopold. He was, by any measure, one of the most honored engineers of the 19th century. But the world he had built was already changing. The problem, from the master machinist's perspective, was interchangeable parts. The idea was not new. Eli Whitney had talked about it in the 1790s. The federal armories at Springfield and Harper's Ferry had been working toward it for decades. But it was not until the late 1800s and early 1900s that manufacturing precision caught up with the concept. As machine tools improved, as grinding machines became capable of holding tolerances that had previously required handwork, as gauging systems became standardized, the need for the hand fitter began to disappear. Henry Ford's assembly line, which began producing Model Ts in 1913, was the death blow. Not to steam engines specifically, since internal combustion and electricity were already replacing steam for most applications, but to the entire philosophy of hand fitting. Ford's system required that every part be identical to every other part of the same type. A piston from one engine had to fit into any cylinder. A connecting rod from one engine had to bolt onto any crankshaft. This was the opposite of the master machinist's world, where every part was unique and every assembly was a custom job. By 1920, the old engine works were closing or converting to other products. The Corliss Steam Engine Company had been absorbed into International Power Company. Watts, Campbell, stopped building new engines and shifted to repair work, maintaining the Corliss engines that still ran in factories and pumping stations across the Northeast. Baldwin Locomotive, which had been the largest locomotive builder in the world, struggled to adapt as railroads shifted to diesel. The company produced its last locomotive in 1951, and the master machinists themselves, the men who could scrape a bearing by feel and lap a cylinder to within 1/64th of an inch, simply aged out. Their apprentices went to work in automobile factories and electrical shops, where the work was different, where the tolerances were held by machines rather than hands, where a man did not need 30 years of experience to do his job. The hand-fitting tradition did not die in a single moment. It faded. By 1940, it was effectively extinct as a commercial practice. What remains today is scattered and fragile. A few Corliss engines survive in museums and historical sites. The New England Wireless and Steam Museum in Rhode Island maintains several, including components from Corliss's own works. A handful of engines still run in pumping stations that were never converted to electricity. Their cylinders still smooth, their bearings still true. After more than a century of continuous operation, maintained by mechanics who learned the old fitting methods from men who had learned them from the original builders. The Watts, Campbell factory in Newark stood for more than 150 years, with its original machinery still on the floor, some of it dating to the 1860s. Wooden overhead cranes and rail systems still embedded in the floor where they were laid in the years after the Civil War. Chad Watts, the great-great-grandson of one of the founders, spent decades trying to preserve it as a museum. He would give tours to small groups, walking them through the blacksmith shop where the same steam engine parts had sat on the same metal rack in the same location since the 1950s, pointing out the fine hand-finished surfaces that his ancestors and their workers had achieved using methods and machines that most of the modern world had completely forgotten. The building was eventually sold. Much of the machinery sits rusted in place, looking for a home that may never come. The Corliss Centennial engine itself is gone. Scrapped in 1910, a few fragments may survive in private collections, but the engine that powered a nation's birthday celebration, that ran flawlessly for 6 months before 10 million visitors, that embodied everything America believed about craft and labor and ambition, was reduced to scrap iron for less than $8,000. If you are finding this worth your time, hit subscribe. I cover the forgotten labor and lost trades that built America, and there is more of this history to tell than any single channel can hold. Consider what it meant to be a master machinist in 1882. You started as a boy. You spent years learning to feel the difference between a surface that was flat and a surface that was almost flat. You learned to read metal the way a musician reads a score, not from a page, but from the sound of the file, the resistance under the scraper, the pattern of blue on a surface plate. You worked 10-hour days, 6 days a week, in a shop that was deafening, dangerous, and dark. You risked your hands every day, knowing that a lost hand meant a lost career and a lost livelihood. And what you produced in that shop, with those tools, was extraordinary. You produced engines that powered the mills, that wove the cloth, that dressed a nation. You produced engines that pumped the water, that kept cities alive. You produced engines that drove the generators, that lit the first electric lights. You produced the Centennial engine that stunned a president and an emperor and 10 million visitors and made a country believe in its own future. None of you signed your work. Almost none of you left any record at all. The engines you built are mostly gone now. Scrapped, melted, forgotten. The shops where you built them are mostly gone too. Torn down, paved over, converted into lofts and apartments for people who will never know what happened on those floors. But in 1882, in Newark and Providence and Philadelphia and 100 other cities, you stood at your lathe or your bench or your forge, and you turned raw iron into precision. You did it with your hands. You did it without computers, without CNC machines, without coordinate measuring systems, without any of the technology that a modern machinist takes for granted. You did it because someone taught you, and someone taught them, and the chain went back generations to the first man who ever put a file to a piece of metal and decided to make it better than it needed to be. That tradition is gone now. The chain is broken. The last generation of master machinists who learned the hand-fitting trade in a working engine shop passed from this world decades ago. What they knew, they took with them, because it was knowledge that lived in the hands, not in books. If you have watched this far, you are the kind of person who understands why that matters. Subscribe, and I will keep telling these stories, because the men who built America's engines never told their own. Every factory engine that turned a shaft in 1880, every locomotive that hauled freight across the plains, every steamship that carried immigrants into New York Harbor, every pumping station that delivered clean water to a growing city, all of it was built by men, like the machinist in Newark, standing at his lathe, working the metal, holding tolerances that modern engineers achieve with million-dollar machines. He did it with a file and a pair of calipers and 30 years of practice. He did not sign his work. Almost no one did. And that is the part that stays with me. Not the engines, not the specifications, not the tonnages or the horsepowers or the bore diameters. What stays with me is the silence of it, the absolute absence of credit. These men built the mechanical infrastructure of the largest industrial economy the world had ever seen, and they did it anonymously. Their names do not appear on the engines. Their names do not appear in the company histories. Their names appear, if at all, in payroll ledgers and apprenticeship rolls and the occasional accident report. I have read the apprenticeship records from shops in New England and New Jersey, names and dates and wages written in ink that is fading now. A boy entered at 14. He earned 50 cents a day. 4 years later, he earned $2. 10 years after that, he earned $4. 30 years after that, he retired, or he died, and his name disappeared from the rolls, and the engines he built kept running without him, and no one remembered he had been there at all. That is who built America's steam engines. Not George Corliss, though he designed them. Not Matthias Baldwin, though he manufactured them. Not the presidents and financiers and industrialists whose names we remember. The engines were built by men whose names we have lost, working in shops we have torn down, using skills we no longer possess. They deserve to be remembered. Not with monuments or statues or plaques, but with the simple acknowledgement that what they did was extraordinary. That fitting a cylinder to 1/64th of an inch by hand is not a mechanical task. It is an art. It is an art that required a lifetime to master, that was passed from hand to hand for generations, and that we allowed to disappear because we found a cheaper way to do it. The cheaper way works. I am not arguing that it does not. Modern CNC machines hold tolerances that would have seemed like fantasy in 1882. But something was lost when we stopped teaching men to feel the metal. Something was lost when we stopped requiring 7 years of apprenticeship before a man could call himself a machinist. Something was lost when we decided that efficiency mattered more than craft, that speed mattered more than skill, that the machine could replace the hand. What was lost was not just a technique. It was a way of understanding the relationship between a human being and the material world. The master machinist did not simply remove metal. He negotiated with it. He understood its grain, its stress, its memory. He knew that cast iron behaves differently on a Monday morning in January than it does on a Friday afternoon in July, because temperature changes everything. He knew things that cannot be written in a manual, because they exist only in the accumulated experience of a working hand. That knowledge is gone. The engines are gone. The men are gone. But for one brief century, from roughly 1830 to 1930, they built the machines that built America. Every one of them by hand. And if you ever stand next to a surviving Corliss engine, if you ever run your fingers along a cylinder bore that was lapped by a man who learned his trade before the Civil War, you will feel something that no modern machine surface has. You will feel the work. The patient, careful, hand-guided work of a man who spent his life turning iron into precision. That is what they left us. Not their names, their work. If you have not already, subscribe. These stories are not finished. There are more trades to remember, more names to find, more work to honor. The machinists of the 1880s built America's engines. They did it by hand. They did not sign their work, and we owe them more than we have ever paid.